Good day and welcome back for the fifth and final installment on evaluating trigonometric integrals. In this video we will investigate two more examples that are a bit involved. So let's go ahead and start off by anti-differentiating cosine to the fourth power. And if you go back all the way to the first video on this topic, whenever we're integrating powers of cosine and sine, we have a nice approach to use. If either the power of sine or cosine is odd, we use a power reduction technique and we're good to go. If both the powers happen to be even, as we have in this case, we need to rewrite using the half angle trig identities. So let me just remind you of these trig identities, and also once again note these are formulas that we have to make sure we are aware of. Sine squared x is 1/2 1 minus cosine 2x. And cosine squared x is 1/2 the quantity 1 plus cosine 2x. So with that in mind, our approach for integrating cosine to the fourth is to rewrite it using these half-angle trig identities with the hope of ending up with an integrand that we can work with. So let's go ahead and see what we can do. So how we can rewrite cosine to the fourth, note that's cosine squared. And comparing to the right, we know that cosine squared can be expressed as 1/2 the quantity 1 plus cosine 2x. So rewriting now, as we've said we are going to, using that half angle trig identity, we would be squaring 1/2 1 plus cosine 2x. And let's just slowly go through the algebra and make sure that we're careful. So first of all, this constant 1/2 is going to be squared. 1/2 squared is 1/4. 1/4 is a constant we can pull in front of the integral. Then what remains inside the integral would be the square of 1 plus cosine of 2x. So foiling that out, we would have 1 plus 2 cosine of 2x plus cosine squared of 2x. And at first glance, it probably appears that we've complicated the situation a bit. We've certainly involved more terms in the integrand, but what we can do is break this up into 3 separate antiderivatives with the hope of evaluating each one individually. And make sure you're careful with this 1/4 out front. It has to be involved in all 3 of these antiderivatives. So 1/4 the integral of 1, that part we can handle. Plus, we have 2/4, where this 2 is coming from pulling the 2 out of the integral, cosine 2x, plus 1/4 the integral of cosine squared of 2x. And as long as we can evaluate each of these integrals individually, we're going to be good to go. And I'm going to note the first 2 are no problem whatsoever. An antiderivative of 1 is x. And an antiderivative of cosine of 2x is going to be 1/2 sine of 2x. And let me give you the quick reminder. This is something I believe we've written down previously. So let's just note it to the side as a common formula. If we would like to anti-differentiate cosine to the kx, where k is a non-zero constant, such as say 2, the antiderivative is 1/k sine of kx. And this is something that you could very quickly check by just differentiating on the right, or you could verify from the left using a u substitution. But if you recall this formula, you are more than welcome to simply apply it. So all that remains now is taking care of cosine squared of 2x. And note this really brings us back to the drawing board. If we're ever anti-differentiating an even power of cosine, we need to go back to our half-angle identities. So that means we need to rewrite this integrand with the hope of being able to evaluate that resulting indefinite integral. Now note there's a subtle difference with this formula. It's cosine squared of something other than x. But note, that's not an issue. In these trig identities, the x is representing just an independent variable. If we rewrite this ever so slightly as cosine squared of something, we would get back 1/2 1 plus cosine of 2 times that something. And in our case, the something is being played by 2x. So substituting 2x into each blank, we would have 1/2 1 plus cosine of 2 times 2x. And a very common mistake is missing that 2x. And I'm going to go ahead now and just break that up into two separate antiderivatives. But of course, to use proper mathematical notation, we are going to write each and every term at each and every step. And I'll note, if I'm able to do this, I think we all certainly are able to do this. So we have 1/4 times 1/2, which would give us a 1/8 times the antiderivative of 1, plus 1/8 times the antiderivative of cosine of 4x. And note, once again, in this case it's cosine of 4x. That's precisely the form that we've already discussed. So one final step. So cutting and pasting the first two terms down, an antiderivative of 1 is x, and an antiderivative of cosine of 4x is 1/4 sine of 4x. And note at this point there are certainly some minor algebraic manipulations. We can combine together the 1/4 x plus 1/8 x. We can multiply together the 1/8 times 1/4. But I am perfectly fine, as usual, leaving it in this form. Note overall the technique or the approach we've used. Because it's an integral only involving even powers of cosine or sine, we rewrite the integrand using those associated half-angle identities. Once we've done so, it might require some algebraic manipulation. It might require multiple steps. We might even have to use that approach again. But we have a template or a blueprint we can follow to evaluate the integral. So let's move on to our second and final example. If we encounter something like, say, the antiderivative of tangent to the fourth, note that doesn't match up with our previous discussion on evaluating integrals with powers of tangent and secant. If the power of tangent happened to be odd, we had an idea of how we can approach the problem. And in this case, since it's just an even power of tangent, we don't necessarily have an approach that we've used previously or something that we're guaranteed will work. But what we do have is the extensive intuition that we've built up. In all of our previous examples, we've somehow pulled off terms and we've rewritten using the Pythagorean identity. So let's just recall the Pythagorean identity. And note it's perfectly fine to start off with the familiar one. Cosine squared plus sine squared is 1. And then dividing each and every term by cosine squared, we can write this as 1 plus tangent squared is secant squared. So let's go ahead and pull off a tangent squared, mainly because that's something we've done previously, and we've also previously applied the Pythagorean identity. So let's see if we can make that work. And as usual, it's definitely worth noting that this is not the only way to evaluate this integral. This is just a way that I think matches up with our previous intuition. So let's see what we can do. So we can rewrite tangent to the fourth as tangent squared times tangent squared. And once we've rewritten in this form of tangent squared times tangent squared, let's go ahead and rewrite tangent squared using our Pythagorean identity. That is, we can replace, and we'll just do one of them, let's say the second one, with secant squared minus 1. And note once again why we are doing this. Even though we don't have the desired form that we've previously seen, we can take that same approach and modify it slightly. Pull off some number of the tangents, and then rewrite some of the other ones using the Pythagorean identity. Now I'm going to go ahead and just see what happens when I proceed and manipulate this algebraically. So if we distribute that tangent through, we would have tangent squared secant squared. And then let's go ahead and make it a second integral involving tangent squared. And at this point, the two antiderivatives are ones that we are able to evaluate. In fact, everything you need to use is currently on the screen. What I would like you to do is pause the video, give yourselves a few minutes, maybe up to 5 minutes, and see what type of progress you can make finishing up this problem. So hopefully you've put a little bit of thought into this integral. If we focus in on the first part, note the derivative of tangent is secant squared. So if we go ahead and we let u be equal to tangent, and this is for the first integral, we would have u squared du. So the first part is actually in maybe the best possible form we could hope for. And I'll take care of the first integral, and then we'll come back to the second one. So we anti-differentiate, and then we go ahead and we resubstitute. 1/3 tangent cubed. Now for the remaining integral, tangent squared. I do not know, say, an antiderivative for tangent squared off the top of my head, but what I do know is an antiderivative of secant squared off the top of my head. So very similar to this previous problem that we've worked through. We use this technique of rewriting the tangent squared. Now we're going to do the same exact thing again. We are going to rewrite this tangent squared in terms of the Pythagorean identity we see to the right. So we can write this as secant squared x minus 1. And note, individually, we can anti-differentiate each term. An antiderivative of secant squared is tangent, and an antiderivative of 1 is x. Distributing the minus sign, we have our solution. So once again, just to reiterate, never afraid to repeat myself here, even though our previous approach doesn't directly apply, that same intuition or technique can be applied. Oftentimes, one of the hardest things with these integrals can be deciding what to do to get started. So in a sense, you really have to be, fearless in how you approach these. You might try something and it doesn't work. That's perfectly fine, because now you've hopefully learned something, and then it's just on down our checklist. What else could we apply? So that completes our discussion on evaluating trigonometric integrals. Make sure you are working problems, and more importantly, make sure you're reaching out to me when you have questions. Stay tuned and take care.